Hello! Today I'm going to be demonstrating MergeSort with this unsorted set of phones, and I'm going to be sorting them by size. So the first step of a MergeSort is to, split our data set into smaller ones until they get to the base case. So we're going to split these in half, split these halves, and then split these. Now we've split this up into our base cases, which is just sorting a one-length list. When we sort this one, well, it's one. There's nothing to sort. Then we do our merging, so we can merge these in order. That's the trick of MergeSort. When we merge things together, we merge them into the right order. So here, this one is smaller than this one, so it goes in front. This one is smaller than this one, it goes in front. We've done our merges. Now we've got these, well, these actually don't merge like that. These will merge into here, because we split into two. And remember, it's a cursor. So now we merge this like that. We merge this like that, and we've got two semi-merged halves. And now we continue to merge back through, so we merge in this one to here, we merge in this one to here, and we merge in this one to here, and it's very fast to sort it. Now, of course, I made some approximations because I was using my hands rather than a computer to do this, so it's a little bit different, but that's kind of the essential concept. We split up the data set, we have each individual thing, we merge them, we merge them, we merge them until we get our merged in order set. And it's very fast because we don't ever compare every single item to every single other item. We just compare them when we're merging them, and when we're merging, we can make certain assumptions because we know that each set that we're merging is already sorted. Like this one is sorted, and this one is sorted. So when we're merging them, well, you can think of lots of different approximations we can make to save ourselves time. Let's take an oversimplified example here that I can show you right now. This one is bigger than this one. These ones are in ascending order, these ones are in ascending order. We know that we can just tack it on like that. That's not the exact assumption that's always made, but that's just an example of how splitting it up into smaller sorted sets can, in like an ideal case, help us, and then the same concept applies in a more complicated way in MergeSort, which we'll see when we look at the code. But that's the general idea of how the sorting algorithm works and its speed. It's much faster than bubble sort because, well, bubble sort has to go through and compare every single item to every single other item. Right, not fast. MergeSort, fast. All right, hope you enjoy, hope it makes it a bit more clear. Oh, and now I should be audible. Okay. Hopefully all the tech is sorted out. I'm trying a bit of a different setup this time, and hopefully it'll work nicely. So we can all see the code. We've got a GitHub repository today. Same GitHub repository as usual. I'll send you guys the link. Today we'll be doing MergeSort. In MergeSort, what we'll be doing is sorting things in a way that isn't slow. Rather, it would be fast. In order to do that, we'll use recursion, and it'll be kind of fun. MergeSort can be a little bit confusing, but we should show how it works, hopefully quite clearly. I've sent the link to the chat now for the GitHub repository we're working with today. It's going to be the same as last time, except if you did get it last time, you're going to want to update because there's going to be a few new files here. Specifically, we're going to be testing the sorting algorithm on the same thing we tested bubble sort on to see if it works properly. So yeah, and we've made it generic this time as well, just to make it a little bit more spicy. So once you've all got that cloned, we can get started, and before you do, I'll just go through kind of the methods we'll be filling in today. So today we'll be working with the public void MergeSort, and then the MergeSort recursive helper method, and the merge helper method. And these various methods have, well, various purposes to help us do our MergeSort. And if we're familiar with how recursion works, we'll understand why there's a number of these rather than just one monolithic MergeSort method. So to start off with, I think I'll go on and explain a bit of the MergeSort method, which is the hiding the recursion kind of visible method that we'll be working with. This is the one we actually call. And this one is kind of the easiest, the least important, and the least cool. And what it does is it just tells it to sort. So I'm just going to say MergeSort recursive, dataset 0, dataset.length -1. That's that. Very simple. So does anybody want to maybe come up on the mic and try to rationalize why I have a separate method for the recursive step and for the public like visible step? Alright, well, I suppose not. In that case, I'll explain it. in a way that's hopefully quite clear. So when we do a recursion, we don't want to necessarily show everybody what we're taking with us at every level of recursion. If you remember from before, when we use a recursive method, we're calling the method from itself, and we're bringing with us certain useful things. So for instance, if you recurse down into a method, you can bring with you, let's say, a counter or a certain, even a string or anything. You can recurse your way into this, and you can improve your results. But when you're calling the method from outside, when you're just a general user, you may not actually want to have the recursive step visible. You might want to be able to do it such that you don't actually see the recursion and you just see the method call. And for that reason, we're hiding it using this MergeSort method. And all we're telling it to do is that we're telling it to sort this array and start from the start and at the end. And it's a really simple method, but it's there to help us out. And hopefully that makes it clear why we have this method. It might seem like a little bit useless. I think some examples show it without this. It's just preferable to have usually, because that is it's helping us do our sorting a bit more neatly. Then here we've got our recursive step. Now this part, similarly, is to do with it's to do with sorting, and it's to do with helping us sort. But we don't actually do any sorting in this method. This method's job is very simple. This method is doing the dividing. If you remember in the little pre-video, I showed dividing the data set, like, you split it in half, and then you split the halves into half, and you split those halves into halves, and then you merge them all together. Well, this method is doing just that. It's taking the halves, and it's splitting them, and then it's merging them back together afterwards. So in this method, what we can do is we can say if the start index is indeed less than the end index, and that's just a check to make sure that you start this off with a reasonable move, and also that if it's of size 1, it doesn't do anything. This just helps us prevent some errors and save ourselves some headache in debugging in case we give it bad inputs. So now the first thing we want to do is we want to find the center of our array, because we want to split our data set in half, and we want to split each half into its own half, and we just split these halves until it gets to the base case. So how do you guys think we could do it so that we could split it into half and then recursively split the halves into halves? Anybody got any idea for that? I'll give you a hint. It has to do with inputs of merge. Oh, sorry, could you repeat? My audio was really low. Yeah, that's right. So we gotta get our middle index, right? So to find where the middle of the array is, we just say let's say int mid index, and I'm just calling it mid index because that matches what the input to the next one is. It kind of keeps it more consolidated, and we'll just say that it's equal to, and I'm gonna do it from the start the average of the start index and the end index, because the start index may not necessarily be 0. It might actually, because this is a recursive method, right? So we might have to divide part of the array after we recurse. We're going to call this method from itself a few times. So sometimes our start index is going to be like halfway through our array, and we'll be splitting in half, let's say, from index 5 to index 10. Then the mid index is going to be between 5 and 10, so it's going to be like 7 or 8, depending on how we do it and how the rounding is done. I think here it'll be the smaller number. But yeah, since it's recursive, we're finding our mid index by averaging our start index and our end index. And you'll see why when I do the next lines. Now, do you want to maybe hazard a guess as what how next we could recursively keep splitting it, or do you want me to peep it out here? I don't know how familiar you guys are with the algorithm here. So. Yeah, that's correct. That's exactly what we have to do. So we just do MergeSort recursive, and then we call it on the data set, the same one as before. We do the start index, and now we end at the mid index. And that is going to continually split the beginnings, like the first halves of the array, right? So it's going to first take, well, now if we run this through, what it's going to do is it's going to take in data set as an input, then it's going to find the middle of it, it's going to go through MergeSort recursive on data set from start index to mid index, and it's going to recursively just take the first half, and then it's going to get us until we get the first element. And that might not be in itself terribly useful, but it will be useful if we also do the other half. So if we do not just from the start index to the mid index, but we also do from the mid index plus 1 to the end index. And this way is going to be recursively splitting it for both halves. And now it's going to do it for each half. Let's say that first you start with 4 of them, right? So you've got 4 things here. Ooh. And then you split the 4 things into halves. Wait, which one is small and it's not visible here? You split these ones into halves, then you split these ones into individual ones, and now you've got 4 individual sets. And we know that when we have something of size 1, it's already sorted. And the point of merge sort is we're trying to divide it into small, already sorted arrays. And the first step of that is to divide it all into arrays of size 1, because each of those arrays of size 1 is already sorted, if that makes sense. Right? So here we've got that step done. And now once we split them all up, well, we have to start merging them. So we have to merge at every step. So every time we split it, we have to merge it again, right? So how can we make it so that we merge it every time we split it? Yes, that is correct. But can you explain why that would actually merge all of them recursively? Wouldn't that just do the merge once at the end when it's all done? Yeah, that's right. Yeah, every time that we call merge sort recursive, at the end we call merge. So once we call merge sort recursive down to the base case, it's going to start calling the merge, and the merge is actually going to be called in the reverse order of the merge sort recursive, if that makes sense to you guys. Because merge sort recursive is going to finish calling completely before merge ever gets called. Because it's going to first it's going to finish recursively calling this one, then it's going to finish recursively calling this one, and then it's going to finish. Then it's going to start calling this one from the lowest level of recursion all the way back up, right? And we'll show that in the debugger. I'll like run it with breakpoints to show you guys exactly what the algorithm is doing. But what that means is it's actually going to start merging from the divided set. So it's going to start the merge when it's sets of 1. It's going to merge them into like sets of 2. It's going to merge the sets of 2 into sets of 4. Right? So the merge is actually happening starting from the smallest, most divided set up to the least divided set. And the split is starting at the least divided and going to the most divided. That's not really a piece of information you're going to like test it on. It's just kind of like it's a tidbit so you can understand more how the algorithm works. Is merge already defined? No, it's not. We're about to define merge right now. And so this is the recursive step of merge sort recursive. Now, merge is the most challenging part of this algorithm. Merge is where most of the trouble happens. It's quite a complicated method because it actually has to do all the sorting. This is where the comparison is done. But it starts off quite simple. First thing we need to find out is how big our subarrays are. So we just say int size of first is equal to mid index minus start index plus 1. That's the size of the first one. Int size of second is equal to end index minus mid index. Also very easy. Now, this is going to be used to create our temporary arrays, because we're going to create temporary subarrays, which we're going to modify, and we're going to fill our data set back up using these subarrays. So to create these temporary subarrays, we just say E, and then it's an array of E, because remember, we're doing it generically now. Last time we did it with strings, and we had this be a string type, but this time this is going to be a generic like helper class which can sort anything that can be sorted. So if you follow along this code and you have a future assignment where you need to write merge sort, you can quite easily reuse this code with this helper and just very easily adapt it to anything that's comparable. You just have to implement the comparable interface, which if we have time I can also show today. All right, so we create our subarrays. So we're going to have a left one, and we're going to call it, we're just going to create a new E, and it's going to be size of first. And then we're going to create a right one, which is going to be the same, E, size of second. Right? Now, what do we do with these subarrays? Well, first thing we need to do is we need to fill them in with the data from our main array. So we'll say for int I equals 0, I is less than size of first, I plus plus. Very easy. We're just going to fill in our left subarray. So left I is equal to dataset I. But it's actually not dataset I, it's dataset start index plus I. Because, remember, we might be working somewhere else other than the start of the array. This could be working in any part of the array. So here we're just copying over the region of... here we're just copying over the region of the array, which is... yeah, come on. I'll figure out that error in a second. So here we're just copying over the region of the array, which we need, into the subarrays. Right, and we'll do the same for the other one. For int I equals 0, I is less than size of second, I plus plus, right, I is equal to, and then it's going to be the data set with the mid index plus 1 plus I, because remember when we passed into this parameter what it means to be the second one is mid index to end index, or like mid index plus 1 to end index, right? And the first one is start index to mid index, so that's where we get these from, like these ranges, these modifiers. That makes sense why we propagate that through like that. The mid index plus 1 comes from the method call here, and the start index comes from the method call here as well, right? Hopefully that makes sense to you guys. If there are any questions, let me know, and if not, we can move on to the next stage. And the next stage of this is to create the while loop to help us actually merge the array in sorted order. And this is actually where the sorting goes down, and we're going to be using the comparable interface here. So this will be kind of your first taste of what that looks like. It's a very easy interface to implement, which I might show if we have some time. So we'll say while index at, or no, yeah, what is it? Oh, we have to actually create these first, yeah. Well, first we have to do multiple indices. So we have an index at left and an index at right, and they're both going to be equal to 0. So index at left equals 0, because we're traversing multiple arrays at the same time. And we'll say int index at right equals 0 as well. And then we're going to say int index at main, which is our big array, or I guess a data set would make more sense, and is equal to start index. And that's because that's where we're starting our traversal, right? So we've created these three indices to help us traverse multiple arrays at the same time. Oh, nice. And my wonderful laptop has lost its trackpad. That is great. Okay, well anyways, we don't need a trackpad. That's nerd shit. All right, so while the indexes are all within the range, so while the index at left is going to be less than the size of first, and the index at right is going to be less than the size of second. So that means that while we are still within the range of both subarrays, we're going to try to merge them together. Now, if you remember from the video from before, what we're doing here is we're actually doing the step of the merge where things are out of order. So for example, here we've got this out of order set of devices here. Right? And when we merge them, we're comparing them to each other while there's still room in these two subarrays. So while these two subarrays are still not empty, we merge these into a main array where, see this one, the first one to merge just goes in. The second one we compare to the first one and put it in the right order. Then we put this one in the right order, and we put them all in the right order. We're basically merging into one data set and making sure that the order is correct at this step. This is where we've got two arrays in memory, and then we're reading off of both of them into the big array. And we're making sure that we read off of both of them in the correct order. Right? And then both of them have to still have something, because in this step we're comparing things. So we have to compare whatever is in index at whatever is in index at left to whatever is in index at right, and we have to see which one is bigger, and then we have to put it in the right spot. So we can say if left index at left dot compare to, and this is how we use the comparable interface, and then right index at right is greater than or equal to 0. Oh, what is it not like here? Yeah. Okay, I'm gonna use a mouse. 1 second. Oh, bloody laptop. Oh. Give me a second here. Just want to see what it doesn't like. Bluetooth is on. What an annoying situation. Give me a sec here. In the meantime, if you have any questions, feel free to ask. I'm just trying to get a mouse working on this computer, because right now there isn't one. Oh, connect. Come on. Oh, you can do it. I believe in you. Let's go. Nice, nice, nice. All right. Okay, I'm gonna switch the output to my desktop computer for a second, so that I'm able to continue on with you. But the code won't be updated, so give me a second. Or I can try to figure out what's wrong manually. All right. Well, while I wait for that to try to sort itself out, I'll keep going with the code here. So left index at left, compare to right index at right. Did I put the wrong number of brackets? No. Okay, I don't know what's up with that. Anyways, I'll write the code and then I'll sort out why the redness happens when I get a mouse connected. Right. So then we can say dataset index at main dataset is equal to index at, or left, index at left. And what I'm doing here is I'm saying that if the one in the left data set here is bigger than the one in the right data set, it's putting it into the main data set there. What I mean by that is, okay, let's say we have our main array here, and we want to add this, and let's say we're comparing it to this. Okay, so this is our main array, these three, and then this one is the one, these two are we're trying to add. So we're seeing, okay, so the main one is already sorted, and we're trying to see if, well, actually, no, the main one isn't already sorted, but these two are already sorted. But these two are the size 1. But we're going to do it with size 1 because I don't have enough hands to do it otherwise. So we can see which one is bigger, this, like the left one or the right one. Well, the bigger one is going to go into the slot because it's going to go bigger to smaller. And then it's going to get into order. And I can show you with the debugger, maybe more clearly, exactly how all that goes. Come on. This is what happens when you use an unreliable device for your broadcast, I suppose. Alright. We're doing the old switcheroo. Just let me check out the right branch here. Master. Check out. And there we go. Alright. Now we're on a different computer, and this one should actually function, and let me do this properly. This one has got a couple of issues on it, but that's no problem. We'll sort those out. So first of all, my library is not imported here. Excuse the technical difficulties with that. We'll just find that. Where is that crap? Hello? RIP headphone users. I can copy paste the code I've copied here so far. Yes, please do that. Yeah, my laptop there just decided not to have a trackpad anymore, so I was unable to click on anything, which is just great. So yeah, let me just find where I kept this tester. It's somewhere. There it is. Don't know which folder that's in, but that's the one we want. And just drag that in there. Okay, perfect. And now we're back up and running, or we should be right now. And yes, thank you for copy pasting that over. Nice save there. I can copy paste what I've merged sort recursive. Yeah, perfect. Alright, merge sort recursive, got that. And then yeah, I'll go back through with the other one anyways. So thank you very much. Let's fill that in. Merge sort recursive, we got its stuff. Get rid of those lines. And merge here has got its stuff too. So yes. Okay, so you just created the arrays. That's perfect. Oh. Yeah, and then I can't instantiate an array of a generic type, which is annoying. But it's okay. Oh, and then this one needs to go there. Yep. Perfect. Okay, that's a really bad fix, but I'll do a proper version later. Anyways, and I'll put that on the GitHub. Now we're going to go through and get back the rest of the stuff we did, which I'll re-explain now. It's a good opportunity anyway. So what we got to do is we got to copy over our data set from our main area into these temporary subarrays. So we can say for int I equals 0, I is less than size of first, I plus plus, left I is equal to dataset start index plus I. Now what that does is it starts filling the left side from the dataset, but starting at the start index rather than 0. Can you please increase text size? Yes, I can. Sorry about that. I was planning to use the other computer for this today, but that didn't work out. So yes, text size will shortly be increased. There, come on. Come on. There we go. There we go. Okay, that's more readable, right? Perfect. Okay, so yeah, we're just going to fill our different subarrays from the main array. So we're going to say again for int I equals 0, I is less than size of second, I plus plus, and we're going to do the same thing with the right one. We're going to say right I is equal to dataset mid index plus 1 plus I. And with that, we are able to, well, fill our data set from both sides. Now, what we have to do is we have to start doing traversal of multiple of these lists at the same time. To do that, we have to start our indexes for all these separate ones. And we're going to start a counter. We're basically starting counters for each subarray. So we're going to start index at left, that's going to be 0, index at right is 0 as well, and that one needs to be a int. All right, and then we're also going to do an index at dataset, and this is like a for loop, but except instead of doing a for loop, I'm iterating through multiple data sets at the same time. So, or I'm incrementing them differently, which means that I will have to do a slightly different style of loop. This is just kind of a, consider it to be essentially a for loop, but it just does something slightly different. So I'm going to say while the index at left is less than the size of first, and the index at right is less than the size of second, and I did the wrong one for the other one. Wrong little triangle there. So while there is still data in both of the little data sets, and that is also whack. So while there's still data in both of these data sets, what we have to do is, well, we have to fill the main data set based on which one should go where from these. All right, so since we're filling the data set from where all of these come from, we're putting it in sort order as well. Now to fill it while sorting, what we have to do is we have to say if, not in here, no, it's got to be in the loop. We're going to say if left, index at left, dot CompareTo. So this is the same as is greater, as just using the comparable interface. It's saying if the comparison of the left to the right at this particular index that we're working with results in the left being larger, we're going to do a particular action. In that case, we're going to add it to the data set. And this way, we're going to add it in sort order in O of n, where n is the number of operations. I believe it's O of n here. Why do we have an indexed data set? Because we're reading from the subarrays, and we're going to be writing to the data set. And you're going to see me use indexed data set right now. So I'm going to say data set, indexed data set is equal to left, index at left. Now I'm filling the data set from the indexed data set. I actually made a mistake up here. It's the data set has to start at start index. Right. So I'm filling the indexed data set is where I am in the main array. The index at left and the index at right are where I am in the like little subarrays, and the subarrays are sorted. So what I'm doing is I'm saying that we start from the left one. We compare it to the right one. We're saying, is the one in the current index of the left one bigger or smaller than the current index of the right one? And we know since both are sorted, if the one here is bigger than the one in the right, it's going to be bigger than all of the ones in the right because, well, it's in sort order, right? So let's give an example of that here, why this will work. Let's say we've got this sorted set here of devices. There are 3 of them, and they're in order, right? And if we know, this is a bad example because I have the biggest one and the smallest one in here. So I'll do a better example. So we know that these 3 are in sort order. And if I compare this small one to these 3 bigger ones, and I put it next to it, I know that since this one is smaller than this smallest of the big ones, it's also going to be smaller than the rest of them. So I don't have to compare it all the way through. I don't have to bubble sort it. I just know that because this one is smaller than these, it can just tack onto there. That's kind of the check we're doing here. We're saying if this one at this index is smaller than the one in the right index, and the right one is going to be sorted because we start from a sorted set, it's going to be able to very quickly determine whether or not it can add. And then we have the index at the main data set because we're going to be doing this for small divisions of it. And so we might be doing this at like, let's say, start at like index 3000 of the main data set or something. Like we don't have to be doing this at the start of the array. We can be doing this anywhere in the array. So index at left, plus plus. Just iterate the index at left, which will help us by traversing the left side. And what's this not liking? CompareTo T, that's fine. Now else we're going to be able to say data set index at main data set, and it's just we're doing the right version now. So we're going to say equals right index at right. Now this way we're saying that if the one on the right is the one we want in this place, we just put the one, like if the one on the left is not the one we want, then therefore the one in the right has to be the one we want because there's only 2 options. And then we iterate the index at the right. And now, after we do all that, we just got to index or iterate the index at the main data set. So index at data set plus plus. And now we finish with this traversal. Now, it might seem like we're done, and actually in some cases we are. But if there is a remaining part of either subarray, like if one is bigger than the other, we can just start by doing, or we can not start, but we can finish by taking the remainder of what's inside of those and putting it into the main data set. So we can say while index at left is less than size of first, and we're just cleaning up the remainder. So if there was something, if like one of them was bigger than the other, or for whatever reason, that was happening, we're gonna fill in the rest from these subarrays. So is equal to left. Index at left, and this will only be called if one of the subarrays is bigger than the other, and usually one of the subarrays is only one bigger than any of the other subarrays, unless you've got some kind of problem, but this is still written kind of rigorously. So index at left plus plus, index at data set plus plus. Right, easy peasy. Now we do the same thing for the right, so we can just copy paste this over. Yeah. And now while index at right, indexed at right, I misspelled that, I'll fix that too, is less than size of second. Yep, you can unmute.
Yeah. Oh, sorry. Yeah, the while loop. Why is it there, or what's its purpose?
Which while loop? There's
on 52.
At 52? Okay, so let's take the case where we have an odd number of things that we split. Let's say we have 3 phones that we're trying to sort, right? Well, we split this up. There's one with one set with 1, and there's one set with 2, right? And let's just say we merge these back together. So in this situation, the while loop we wrote above is going to be able to iterate through until both of these have stuff in them, right? So it's going to, let's say that it puts this one in, like it puts this one of a size 1 into the main data set. Now it's going to exit that while loop because index at left is no longer less than size of left, right? So these two are remaining and they're not in the main data set. And that's why we have this while loop, so that we can clean up the remainder. It helps
makes
us
sense.
In that situation, yes. And the reason we have a while loop is it's possible in some cases that we have more than one remaining. And then we have to do the same for the left and the right, and now we just say index at right plus. And now this is the full merge sort part of MergeSort. This is really all the algorithm is. Now we can figure out if it works. And there's just one thing we do need to sort out here, and that is the fact that I've made a typo in indexed, and I want to sort that to index. So in IntelliJ, if you want to rename something or Eclipse, you can do refactor rename, and then it'll rename all occurrences. So now I can just get rid of the typo here. No, index at right. And now, in all cases, it's going to be not misspelled. Okay, now hopefully this works. How do we know if it works or not? Well, last time I think I wrote a test in this. Do I have this test still here? Oh no, we never even we don't even have this one, so it's not going to work right now. Again, we want to start our recursion by just saying MergeSort recursive dataset 0 dataset dot length -1, and that just tells it to start the recursion at the whole dataset. Now, if we want to test our results, we can see if our MergeSort works. So let's try it here. Arrays.sort, sorting algorithms dot MergeSort. All right, test sorting will be called. Now let's see if it runs from the main. It may not. Last time I had a bunch of little null pointer exceptions and stuff because it's kind of a tricky thing to write. There's so many indices being thrown around. Let's see if it works this time. Oh, yeah, I'm just going to minimize that. Scroll all the way up. All right, perfect. Well, it didn't tell us that there was any kind of error, which is nice, because that means that it actually sorted properly. See, what I do here to do my test is I compare arrays.sort to sorting algorithms.mergesort, which are kind of equivalent methods now. And I can see that, well, there are no errors found, so it's indeed sorted it properly. Now, if we want to do another test of our sorting, I've also supplied image0gui.java here. And if we run this, I can show you guys how to use comparators. And oh wait, well actually yeah, before I do, I'll do what I promised and show you guys a runtime efficiency, see if our MergeSort is actually faster, and I'll show you with the debugger. I don't want to get ahead of myself. Still got a bit of time. But afterwards I can show you the interface for comparable. So to go into MergeSort, I'll run it with the debugger, and I'll show you how it runs. And then I'm going to show you the speediness of it using the speed tester. But well, right now I just have to close the speed tester because my computer seems to be lagging. All right, so close that crap. Why is my computer lagging right now? I don't get it. Yeah. Oh, the CPU is being used by something. No, I have absolutely no clue why it's lagging this much, but oh well. Okay, anyways. So we go through here. We go to, well, I'm going to put a breakpoint on my MergeSort recursive. Well, actually, no, I'll put my breakpoint on MergeSort. And I'm going to run this with the debugger, and I'm going to show you guys how this thing works. So right now we're going to be sorting a data set of size 10, so it's not going to be too much. And here in my debugger, I've got options step over and step into. Step into is going to take me inside the method that I'm calling. So if I click step into, now I'm inside of MergeSort recursive. And we can see that start index is 0, end index is 9, so we're doing the whole array. We're going to go to the next line. Mid index is going to be the middle of the array, so it's going to go from index 4 to 9. Now it's recursively calling this from 0 to 4. Now if we enter this method, now it's doing the same thing again, but now it's going from index 0 to index 4. And it's going to keep doing this over and over again for every subindex until we eventually get to size 1. Until we get to the situation that we are merging. So we'll step over. Right now we're in the second call to MergeSort recursive. We're going to step into that. Now we're going from index 5 to 9. We're going to step into this. Now notice how the indexes are getting closer and closer together. So we're getting closer and closer to a list of size 1. We go into the next step. Now we're going from index 5 to 7. We go next. Next, we go in. Now we're going from index 6 to 7. Now we're going next. Next. Now we're going in here again. And now we're just going to a size 1. So notice in our different levels of recursion, and in IntelliJ you can see levels of recursion here. They're numbered. So here we've got 5, 4, 3, 2, 1. We've got our 5 levels of recursion. And we go through. In our first level of recursion, we've got our full data set. Well, I guess this is our full level, first level of recursion. We got our full data set. Then in our second level of recursion, we've got half our data set. In our third level of recursion, we've got even smaller part. And we keep recursing until we get to a data set of size 1. See here? The min index is 5, so it's between 5 and 6. Right? Does that make sense? We're splitting it until it gets to size 1 at all these levels of recursion. So now at our deepest level of recursion, now this condition is telling us, oh, we have a list of size 1. It's impossible to recurse any further. And it's just not going to do anything. Right? So we don't care about this step. We're going to step over. We've broken out of the deepest level of recursion now. So now we're back at recursion level 4, the second deepest, where it's of size 2. Now we go next step, and we're going into merging now. So now we're merging a very small size 2 array. So we're going from index mid to 5 and start to 5. So we're merging two things of size 1. It's two things that are very small. Now how do we merge two things of size 1? Well, we're creating two arrays of size 1. We're filling the arrays of size 1 with all these things, right? So we're filling our temporary arrays. Now we've got two arrays of size 1, which we are reading from. But notice here, I remember somebody asked before about the indexed dataset. That's important because here our indexed dataset is something we're directly accessing. So our indexed dataset here is not 0, right? It's the start index. So we need to keep track of it separately than we keep track of these indices, because remember, these two are arrays of size 1, so they have no index 5. It's the main dataset which we're working in right now. So we're taking two arrays of size 1 and storing them into like index 5 of our main dataset. So now we keep going, we go through, we hit the comparison step. Now we're going to see, yes, both of the arrays have stuff in them. Now we're going to compare them. We're going to say, okay, so which one is bigger, the left or the right? Turns out the right was the bigger one, so the right is going to be put into the main dataset at that index. And now we can no longer sort because we have one of the different comparable ones is empty. So now we're going to go into our helper loops, these ones, which clean up after we're done. Now these ones are going to help merge this stuff back in. Index at left plus plus. Now this loop is no longer running. This loop is no longer running, and we've successfully merged these two. Now we've still got 5 more levels of recursion to go through to get these things merged up. Why do you start at index 5? It's because this recursion that it did was doing the second half of the array. So I did. It's just the order at which I stepped into. I stepped over a few times just to show you guys a step over, and then I stepped into the recursive method when we were already at index 5. I started showing you it halfway through the sort, basically, if that makes sense. Or actually, I started showing it to you at the start of the second half of the array.
Makes sense.
Yeah. Perfect. All right, so yeah, we go through, we step over, and it just repeats this process. I'm going to go it a few times until we've merged up and until we have a bigger range that we can work with, and we can see a merge happening on something bigger. So right now our end index is 9, our mid index is 4. This looks like a good merge to watch, right? Because it's happening between a larger data sets. So we're going into here. Let's see, what are the sizes? 5 and 5. So this is the last merge of the merge sort. We're going through, we're going to fill our data sets, just spam through that. I get it, we're filling the subarrays. All filled up. We start at 0 indexes, and now notice that since this is the last merge, we're starting at index 0 because we've already merged them. Now let's quick detour while we're doing this. Our left and our right are, I guess it's hard to tell that they're sorted because I'm using strings, but these are sorted alphabetically right now. And I'm using like these weird characters, so it might not look like it's alphabetically sorted, but it is. These are in sort order. So left and right are both sorted. It's my mistake, I didn't give something easy to identify as being sorted, but if we look at the Unicode value of the one in 0, it's going to be, 81, and the Unicode value of the one in 1, well, it's 106 actually, that's weird. I guess because the string comparison is, it's using CompareTo on the string, using some strange stuff, or maybe it's in reverse order, that's also possible. Yeah, this one's minus 120, so I think it might be in reverse order. Regardless of the way, it's sorted in accordance to CompareTo. So it's as sorted as it gets by this comparator, which is the CompareTo comparator for this kind of object. So these are sorted, left and right. These two subarrays are in sort order. So we go into here, we start this traversal. We're comparing them. Is left or right bigger? Here, left was bigger, so we're putting left in that index. Then, okay, here, right was bigger, so we're putting that in the index. We go through and we put left or right depending on which one is bigger. And this way, notice how we only ever compare one of the left ones to one of the right ones. It's kind of like, we could use a stack and a queue for this if we wanted to, technically, right? Because we're just only looking at the one on the top. We're only looking at the most recent one. We're comparing if the one at the at the current index of the subarray is bigger or smaller than the one at the current index of the other subarray. And the one that's bigger gets put into the main data set. That subarray gets iterated, so that one like essentially gets popped, and then we look at that next index. But we only ever compare one to one. We never compare the whole data set to each other. We only ever compare one thing to one other thing. So now we go through, and we finish that up. We just put these in sort order. We're basically just seeing which one is bigger, inserting the one that's bigger into the right spot, then sorting it through. We're getting to nearly the end of the data set. We've just got a small cleanup to do with something in index 5. We actually had a few on the left side, which were already there, because I guess the left one had the biggest ones. So this is like the biggest ones being tacked on at the end of the list. So imagine that if I did have these like unsorted ones, let's say I had like this big sorted end. Would there be any disadvantage of using a stack? Yes, there would be a disadvantage of using a stack, and that would be that you would have to bother with a stack. Like an array will be instantiated faster, I think, in this situation. Well, not even faster, but an array would be perhaps more efficient because first you're able to access it at any arbitrary index, and you could do it with a stack, and it probably wouldn't actually be slower. Really, it would be just harder because you'd have to fill up a linked list, and you'd have to create more objects. Like, it'd be less memory efficient, I think, because the array is just storing like a block of memory with variables. A stack has like references and stuff, so I think that the array would actually be more memory efficient. And I think that the array is just less hassle to work with because you're working with indices, whereas with push and pop, you could do it. It would be a similar number of lines, but it might be a little bit more confusing because you're working with an array and a stack at that point. But if you want to do an exercise, try with a stack. I think it'd actually go pretty well. But it's not really conventional. It's possible though. I just put the stack and queue example because you think about it, you're only accessing the most recent one at a time. So that is that. Now, I don't know of anybody who's done it with a stack. So now we've finished our merge, and we've got our sorted array. So that's MergeSort working in, in its recursive manner, and sorting the data set. And now, I could actually show this better if I ran this from image viewer GUI, where it's going to sort colors, because I can actually show colors being sorted visually. So I'll click hard on that, so it sorts these hard ones. Oh, I didn't run it with the debugger. Oopsies. Yeah, debugger, huh? So now we're going to watch it sort colors, and I think sorting colors might be a bit of an easier demonstration because colors are visibly, it's easy to tell when they're in order or not. So stop and rerun, come on. Hard. Let's go. Okay. So our data set is of size 6. Our data set has colors in it. They are these colors. We're sorting them by RGB value. So now if we jump in to the recursive sorting, and we're just going to step over, and step into. Okay, let's look at the merge that happens here. So right now we're merging part of the array. We're going from 3 to 4. Data set, size of first is 2, size of second is 1. So we're merging one of size 2 and one of size 1. This is where it's kind of lopsided. We're copying over the data first. The data copying is very obvious, so we'll just skip through all that. And we'll start at the while loop. So here, we've got our left and our right. Now notice how these are both sorted. I think it's being sorted in terms of RGB value, so the one with more RGB value is first. So the light blue is worth more than the gray, and the orange is worth more than the nothing, because, it's size 1. So we go through and we compare. So here, left, actually it even shows you here in the debugger. So right at index at right is going to be the orange. Left index at left is going to be the blue. The orange is worth less than the blue because it has less numbers for the RGB value. So let's see what it chooses. It's going to go in here, and it's going to say that the left one is preferable because the left one is bigger. So the left one gets shoved into the data set. And now we still have stuff left in our data sets here. So we're going to compare our gray to our orange. And our orange is worth more than our gray, is it? Yeah, I think our orange is worth more than our gray. So now it's going to do the same thing again. And now it's emptied it out. It's going to clean up. And there it goes. And now we can see that in our data set, this little section is sorted. The blue, gray, orange block is sorted. CompareTo returns a negative number when this is more than the input. CompareTo, well, you can actually see the documentation on CompareTo, where it describes it quite well. So if we hover over CompareTo, yeah, click documentation. No, come on. No, okay, I'll just type something.CompareTo here. I'll show you the documentation for it, and that makes it the most clear. So e.CompareTo. Oh, not e dot. Let's just say dataset 0. I'm just doing this as an example of CompareTo to show you the documentation. This is not actually part of the code. So now if I go quick documentation here. So what it does is it measures how different these different things are. So yeah, where is it? Yes. So yeah, it returns -1, 0, or 1, whether it's the difference is negative, positive, or 1. So for numbers, it will in fact return a negative value if one is like smaller than the other, right? But for something like color, it's more abstract as to what the heck it does, because you don't know how you're going to directly compare colors. So what I do in my CompareTo definition is I actually turn the colors into numbers so that I can compare them. The way I return a negative if the difference is negative, or a positive if the difference is positive, is in here I implemented comparable for color. And I said here that the output is the color's RGB minus the difference between the RGB of the color and the RGB of the other one. Where is it? CompareTo. Where is CompareTo color C? Oh, did I not have it? Oopsies. My comparable was... Oh, no, it's here. Yeah, it is. So, CompareTo with color C compares a color by its RGB. So it says this color versus color C, which is just any color you pass in as an argument. It gets the RGB value, it subtracts them. So it says if this one, if the one you're comparing to has more RGB, then it's considered a negative result. Now that's arbitrary. I just defined that myself. I could also reverse the order of these and have it work differently. And comparable is kind of like, you have some freedom in how you're supposed to implement it. Like, the way you're supposed to implement it depends on how you feel like your data set should be sorted. So if I wanted to make a randomizer, I can make comparable just return a random number. If I wanted to make like something that sorts things in reverse order, I just could reverse what the comparator does. Does that make sense to you guys? Like, it's kind of up to you what it does. But here I'm just doing a subtraction of RGB versus get RGB. And yeah. So that's what CompareTo does, and now it's sorting my colors, and the little section of the data set which we were working with is now sorted. And we go through, and we keep sorting it, and eventually the whole data set will get sorted, and we can see it reflected here. And that is the function of MergeSort. It's that we compare. Well, actually, I think my sorting algorithm might not actually work, or not my sorting. My comparator might not actually work right now for the color sorting, because I might not actually call the correct method if O instance of color return this dot compare to. There. Now this, it should overload it. It should call this one when you use a color, but I'm not sure if it was doing that because it didn't look sorted to me. So I'm just going to double check that it did in fact work properly. Come on, rerun. Alright, give it a second. And yeah, that's comparator, that's MergeSort. I'm just going to do my last check here that it worked properly. And then if you guys have any questions, I'll be happy to answer. Yeah, that... Okay, it looks like the same, so my overloading did actually work just fine, as I thought it should have, just making sure that my overloading was working fine, because the result looked a little bit weird. That's because RGB comparison can look a little bit strange. Anyways, that is the MergeSort test. Now if I show you the runtime efficiency of it, I'll just leave that graph up, and then see if you guys have any questions. I'll compare the bubble sort, MergeSort, and that. Okay, so if you have, isn't white supposed to be at the start or the end? Yeah, it is. That's why I'm thinking it's a bit weird. I think the white might actually be a glitch in my GUI. I think that might not actually be a color that's in the dataset. I think that might just be the window color, because the dataset might not be filling the window. That's my hypothesis. It looks like it is actually sorting it because I can see that it is calling the CompareTo, but the CompareTo with the RGB looks like it's doing a bit of weirdness. Also, I think it might use int overflows, so when it has 255, 255, 255, it might actually overflow and consider it to be very negative. That's something I don't know, I'm thinking about what it could be. If I want to really be rigorous, I can just make it like compare red, or compare green, or compare blue, and that way it might work a little bit better. But yeah, here are our different runtime efficiencies for our different sorting algorithms. Our merge sort is the yellow, our insertion sort is the orange, and our bubble sort is the green. And if I increase our steps per iteration, we can see that our bubble sort and our insertion sort just skyrocket, and our merge sort stays quite on the floor. If I refresh that as well, it should be quite clear that indeed our merge sort is a heck of a lot faster than the alternatives. So yes, if there's any more questions, I will be happy to answer, and yeah. What does steps per iteration mean? Okay, this is part of the runtime tester. This is the same one as assignment 2. Steps per iteration means that it is increasing how many things get added to the data set every time that it takes a step. So here the steps per iteration is quite high, so it's doing 4,365 items every step, right? So from step 1 it was at 0, then it went to 4,365, then 8,370. It steps up by like 4,000 things every time, right? Step time is for math methods, so these math demos, it's like a constant factor. If you remember the equation for runtime efficiency, there's like a factor, like a multiplicative factor that you can use. That's the step time. It doesn't apply to these methods. It only applies to math, like ideal math methods. So yeah, turning up the steps per iteration very high is like taking the limit in math of the size of the data set as it approaches infinity, because we're increasing the size of the data set much faster. So imagine that this is taking the limit as n approaches infinity, and that will really exaggerate the differences between O of n log n, and O of n squared and stuff. And here we can really see an exaggerated difference between the various differently fast sorting algorithms. And MergeSort is clearly dominating. Alright, and now just to make sure that our color thing isn't totally weird, I'm going to change the comparator to compare redness instead of RGB. That's one of the good things about comparator. It's very generic, so I can just say get red instead, and then this is just comparing it by a different quality now. Now instead of comparing the RGB value of the color, it's just comparing the red channel of the color directly. So if I rerun this, not sorting algorithms, I want to run image viewer GUI. If I rerun image viewer GUI, it should now sort it by how red all this stuff is. Okay, so now it's sorting by order of redness, I believe. I don't know why it's being a little bit weird sometimes, but that is what it's doing. And in our sorting algorithms.java, yeah, we are indeed doing that. All right. In that case, I think that should all be hopefully good. I'll see you guys later then, and enjoy your day. Hopefully this MergeSort will come in useful for your future classes. There is a complete MergeSort in the solutions branch of the GitHub, which was done from Monday, and there will be there's 2 solutions branches. There's Monday solutions and there's Thursday solutions, and from those you can just look at the completed code. Enjoy your day, and see you guys later. Bye bye.